Sorry about that. So that's our break-even quantity. But remember, for me, I always want the two pieces, and on the quiz, I actually very much specifically say break-even quantity, break-even price. But so we want the price here as well, and remember, to get the break-even price, you plug it into revenue or cost, whichever one makes you happier. I always choose to plug it into revenue because it's usually the easier function. So 30 times 2,000 is, well, doesn't that get us right back to, wait, hold on. That gets us right back to 60,000. Okay. What have I done? 50. No wonder. Thank you. I'm pulling the wrong freaking number. I was looking over here. Sorry, our revenue function was 50 times 2,000. I thought that was really weird that that was coming out to be 60,000. So sorry. Oh Lord, what is that? 100,000? Sorry about that. So that would be our break-even price. So our quantity was 2,000, price was 100,000. And yeah, thanks for calling me out on using the wrong number. Questions, concerns on that piece? Alrighty. Now, I know today's Wednesday, so that meant that most of you viewed the stuff on your own on Monday because there was like a whole 10 of you in class, but it was optional. I'm just babbling. Anyway, so I know the exponential stuff was kind of on your own, but in terms of the quiz that you're going to take at the end of class, this, as long as you're comfortable with this, you'll be fine. So, scroll down a little. A bacteria population starts with 2.75 million bacteria and grows at 5% per hour. Find an exponential equation to represent the amount of bacteria after 2 hours. How many bacteria are there after 3 hours? So for exponential functions, we're always looking for some p naught a to the t, where p naught is our initial value, and the initial value we start with here, we're told we start with 2.75 million. So we don't have to write that as actual million. I mean, you could if you really wanted to, but I advise against it. Just keep the unit on there when you're keeping track of things. And then we're told that it grows at 5% per hour. But remember, with exponential functions, there's an a value, but then that's made up of 1 plus r. 95% of the time, you're given the r value, not the a value, which is what we have here. Because it's given as a percent. If you see the word percent or the symbol, or you see the word rate, it's talking about the r value. If you see the word base, it's talking about the a value. That doesn't happen as often with these word problems. The a value is usually more found when you're given 2 points or you're given a table or something like that. When we've got these word problems, we're usually given r. But we also have to convert it over to a decimal, so that's going to be 0.05. So equivalent to 5%, just to clarify. So that means our a value is 1 plus this 0.05, so 1.05. Now we have the two pieces of the equation we need. We just write the equation. So the equation I'm looking for is 2.75, 1.05 to the t. Questions, concerns about that before I finish it? Because technically I haven't answered the last bit of the problem. Okay. And then we're asked for the population after 3 hours. Well, since t is in hours, we're just going to plug in 3. So we're going to find whatever the heck 2.75 times 1.05 to the third is, which should be about 3.18, and this would have been in million bacteria. Yeah, I think that was the fuller, yeah, 3.1834, exactly. I rounded to 2. In terms of the quiz, rounding at least 2 decimal places is usually my idea. 3 is kind of better, but as long as you take 2 or 3, You should be fine. Questions, concerns on the warm-up? I always forget I have a mic on. All right, if you feel okay with that, you'll be okay on the quiz. So if you have a question, now's your chance. 5, 4. Okie dokie. Well, then we're going to go over to 1-6 notes then. So 1-6. What is happening? Go back. Go back. Go over here. And then 1-6. Yeah, it'll be on Blackboard when the quiz actually starts. So it's not there yet, but at the end of class, it will pop up on Blackboard in the assignment tab. So the natural logarithm is, no, you don't have to use Respondus for quizzes. So the natural logarithm is all about what 1.6 is about. That was bad English, but anyway. So suppose we have the following situation. We have the population in Nevada in millions can be modeled by the following. So we have that equation to model the population. And say I asked what the time value would be if the population was 4 million. Well, you'd be trying to solve, I gotta remember, never remember to set this up right. Well, then if we plugged in 4 here, I don't know why there's the extra 0, but I'll keep it around. The thing we'd want to solve for is in an exponent. How the frickety frackin' heck do I get into the exponent to be able to solve for it? That's the point. We need something that allows us to essentially get that exponent, and what's going to happen is we're going to be able to bring it down. But we essentially need something that's going to undo that exponentiation so we can actually solve things like this, because we want to solve things like this. So, definition. The natural logarithm which is also written ln of x, that's an L, not a 1, is the power of e needed to get x. And I should probably have my notes out. That would be smart. So what I mean by that, it's not super imperative that you remember this definition. It's mainly that you want to remember how to do it, but essentially how to use it, I should say. But essentially what this is saying is that if the natural log of x equals some value c, then it must be the case that e to the c equals x. That's what I mean by the power of e needed to get x. We're not going to use that idea as often. We're going to use a lot of these properties that we're going to talk about in a hot second. But that's the idea behind it. The natural logarithm is also sometimes written as log base e of x. And note that the natural log is not defined for 0 or negative numbers. So if you were to try to plug in natural log of 0 or natural log of negative 2 into a calculator, it would put out an error message for you. Also note, on your calculator, those of you who are here can see me holding mine up. Not that you can see much of it, but anyway, there's an LN button, usually in the leftmost column, but there's an LN button, and there's also a log button. If you don't know what the log button does, don't use it. Just use the LN button. In terms of this class, mainly for time purposes, we don't go into other log bases. We just talk about the natural log. So in this class, we only talk about the natural log, not any other log bases. If you know how to use other log bases and you want to go ahead and use them, go ahead. I don't care, as long as you're using them correctly. If you know how to work with other log bases, whatever floats your boat. But in terms of this class, everything we need to do, we can do in terms of ln. So we're going to just use the natural log for everything. Is that better, Catherine? Can you see it now? Oh, she's gone. She's gone from the call. I'm gonna keep going then, I guess. Oh no. Can you see it yet, Catherine? Now that you're back? Still no? Let me try one more thing. Hold on. What about now? Okay, awesome. Isn't this such fun? Alright. So I'll try to keep as much of that as possible on there while I write this next thing. And now it's going to lag. Now the lag starts. Thank you. That was cool. Okay, so we've got some properties of logarithms as well. So we essentially have, if we have the natural log of two things that are multiplied together inside the logarithm, we can split this up as the natural log of A plus the natural log of B. If we have two things that are divided inside the logarithm, we can split this up as natural log of A minus natural log of B. If we have the natural log of something to a power, and this is the big one, because it's used to help us solve the things that we need to solve, we can bring the power outside of the logarithm, which is why these are useful. Those three are kind of the powerhouses. Those are the main ones, but a couple more. We have the natural log of 1 is 0, and the natural log of E is 1. So remember, E is a number. It's 2.7828, blah, 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 blah. And then two more that we use even less, but just so that we know them. If you have the natural log of e to the x, that's just going to be x. P just stands for a power. So any power, whether it's a variable or not, it's just something in an exponent. It can be whatever we need it to be. And also, if we have e to the natural log of x, this also just results in x. Whoa, what happened? Blink. So I'll pause for a minute while you guys get those down. And then we'll see a couple examples of using these, and then we'll go on to see how we're going to solve equations using this natural log. So I'll try to, I can keep them in for this first example. Let me move this over. All right, so say we want to use logarithm rules to condense the following. So we essentially want to take this thing and we want to write it as the natural log of just one singular thing. So when you're condensing, the first thing you want to focus on is powers. So essentially this rule that's starred above. And after you've dealt with the powers, you'll move from, so work left to right for the addition and subtraction rules. If you're used to this and you know how to work with them, you don't have to work left to right as long as you're careful. But if you're not used to working with these, I'd highly suggest just working from left to right. That way you won't get it wrong accidentally. So say I want to condense this. So I'm saying that the first thing we should deal with is the power rule, if you will. Maybe I shouldn't call it that, but the thing that deals with powers, the one that's starred. So the first one I have is this 3 natural log of x. Well, my rule, so I essentially have this right side and I want to go backwards to the left side. So what it tells me I can do is it tells me that I can pull in that number into the power. So it becomes an exponent inside of the logarithm. We don't have anything to do with ln of y yet. but I'll just do the powers all at once. We then have this back here. Now, if you wanted to, you could treat that as a -1/2 and bring the entire -1/2 in, and then it would turn into addition. I suggest just taking the number and not the sign, but you can technically you can take the whole entire sign and you'll still be correct. It just might look slightly different than someone else's answer. It's the same algebraically, but it just might look different. But I personally suggest just taking the number. So I would say minus natural log z to the 1/2. Take that 1/2 in as the power. So now that you've dealt with the powers, we've brought all the numbers on the outside into exponents. We're going to work from left to right and use our addition and subtraction rules, these kind of first two up here. So the first thing I come across is an addition between the natural log of x cubed and the natural log of y. So my rule tells me that I can combine them together to the natural log, and then I multiply the things that were inside the log. So I have x cubed y. I'm going to run out of space. Let me write that a little bit smaller. Natural log of x cubed y. And again, if you get really good at these, you can kind of do these all in one step, or you can kind of jump around. But if you've never seen this before, or you're super rusty, just take it one step at a time. So now we have this natural log of x cubed y minus natural log of z to the 1/2. Well, if we have subtraction, then we can bring it together into one log where we divide the things that were inside the logarithms. So we end up here. Side note, if you had made it z to the -1/2, what you would have gotten would be the natural log of x cubed y z to the -1/2. These two things are algebraically equivalent. That's what I mean. They're algebraically equivalent. They just look slightly different. But if you prefer one way over the other, whatever floats your boat. Anyway, questions, concerns on that? Alrighty. So let's go the other way then. So I have to make the rules go away, sorry. But now we want to expand. So we have one logarithm and we want to make it a bunch of logarithms. So when expanding, you essentially do the opposite. You focus on, now this one's harder to say. So you focus on the, I'm going to say multiplication, addition, and division, subtraction. So I'm linking those together because the multiplication inside becomes addition. Based on, I'm going to say outside operation. What the flying heck does she mean by that? Give me 1 second and I'll try to make it make more sense. And once you've dealt with all of those, then you deal with the powers at the very end. And it's lagging again. There we go. What do I mean by outside function? Outside operation. It's a tiny bit tricky, and you just kind of got to get used to it. So in this one that we're working with, I ultimately have something divided by something else. That's kind of like the outermost thing that's happening here. We have multiplication in the numerator and multiplication in the denominator, but like the outermost thing, if you will, is the division. Whereas say I had something that was like 2x times y over z cubed, and it was in a natural log. I have division there, but kind of the outermost thing that's happening is this multiplication right here. So we'd have to take care of that first. Does that kind of make sense? So it's kind of like you're looking to see what's happening on the outside, if you will. I never know how to explain this part well. Just kind of takes some practice. But so the first thing we essentially want to deal with in this example is that division. So we ultimately have something divided by something else. So our logarithm rules tells us that we can split that up with subtraction. And what is going to go in each one is going to be the numerator in one of them and the denominator in the second one. So we have, 2x and y z to the fourth. And again, this is, once you get good at these, or if you know how to work with them super well, you can kind of jump straight to the next step. So again, if you already know how to work with these and you're savvy, you don't have to do all the steps if you don't need them. But I'm trying to break it down in all the tiny little pieces. So now what we would deal with is, so let's just focus on this first term first. So natural log of 2x, well, that's still something multiplied by something else, 2 times x. So we're able to split this piece up into 2 pieces, broken up with addition. And the 2 goes to one of them and the x goes to the other. And since I'm doing this just one step at a time, let me just leave the other part alone then. And then I can focus, so essentially this first piece is done, this second piece is done, I've got nothing else to do. So I'm done those 2, so I can kind of, this last piece, I have some multiplication there as well. So once again, I can break that up into addition, but you want to be super careful. Anything that you break up that came after a subtraction should get put in parentheses or brackets, because you're going to need to make sure everything gets a negative. The negative is going to have to distribute through. So this would break up into the natural log of y plus the natural log of z to the fourth. Again, if you get good at these and you just want to jump straight and you kind of realize the distributing is going to happen and you just want to jump straight to subtracting both of them, and you can kind of make that jump, go right ahead. But anyway, and then there's one tiny last thing we need to do here, is we need to deal with that power that's on the z to the fourth. I can't scroll that way, I always forget. So the last thing here, the natural log of 2, we can't do anything to. Natural log of x, we can't do anything to. Minus the natural log of y, we can't do anything to that. But then here we have that power of 4, which we can bring outside the natural log. Savvy? Questions, concerns? So that's kind of how those rules are used. We can expand and condense things. The more important thing is, I'm going to take the next couple minutes. I know I'm starting to run low on time, but I want to get to the first 2 examples on this next page. The more important thing, why did you make the second one? Right. So let's see. First off, if you're ever going to split up something with that has multiplication in it, but it came behind a negative, that should always go in parentheses because we need to distribute that negative through. Another way that might help you think about it, that z to the fourth started in the denominator, right? So we kind of have to make sure it quote unquote stays in a denominator, if you will. And since the division, everything in a denominator, since this rule tells us that the denominator gets subtracted, even if the denominator has multiple pieces, each piece of that denominator should be subtraction, if that also makes any more sense. So essentially, if we have a denominator, if we have to break up that denominator any further, we need to make sure that that negative gets distributed, because we need to account for the fact that it came from the denominator of the original piece. Does that make any sense? Okay. Any more questions? All right. Process for solving equations using logarithms. So I'm going to fill this out. We're going to do the first 2, and then we're going to take our quiz. So if you want to solve equations using logarithms, the first thing you're going to do is you're going to isolate the exponential term. So essentially that means you should have some a to the x equals p. There shouldn't be anything else connected to that term that has the exponent. It should be completely by itself. After you isolate it, you're going to take the natural log of both sides. This is essentially the step where if you know how to use other log bases, you are free to use them. So take the natural log of both sides. So essentially we get natural log of a to the x equals natural log of p. Bring the power down. Using log properties. And just the one log property of being able to bring that exponent down. So we'd end up with something that looks like this. And then the last thing is that you've essentially finished solving for x or whatever variable you're working with using algebra techniques. So in the above, we'd essentially just have to divide both sides by the natural log of a. And that's how these are going to work. So I know, again, I'm slightly running out of time. First two are going to be pretty quick, so I'm going to take some time to do them. I'll give you a couple more seconds to finish writing those down. So say we look at this first one in this example 3, we have 3 to the t equals 10. Well, the first thing I have to do is isolate the exponential term. Done. There's nothing next to that 3 to the t. There's nothing I have to kick over to the other side. I'm already done that step, didn't have to do anything. So now I have to take the natural log of both sides. So I have the natural log of 3t equals natural log of 10. Next step is to bring that power down outside of the natural log. And then finish solving for t using algebra techniques. Well, to get t by itself, we need to get rid of that natural log of 3, so we need to divide both sides by natural log of 3. And this is approximately 2.096. In terms of Wiley, I'm pretty sure they'll always want the decimal. If you leave it like this on an exam or a quiz for me, that's perfectly fine. It's technically correct. Double check the instructions to see if I say write your answer as a decimal, but usually I don't really care. So super quick, this next one, I do have to isolate this because I need to get this 8/6 to the t by itself, so I need to divide both sides by 5 first. So if I, divide both sides by 5, I get 8/6 to the t equals 5. I'm going to run out of space. Take the natural log of both sides, because we now have it isolated. We can bring that power out, the entire power. Nope, I'm not even going to. There's another way you could do this. If you see what it is, go right ahead. But if not, just take the whole entire frickin' power down. What up?
How is that considered isolated now? Like t isn't by itself.
We don't want to isolate t yet. That's the goal. But to get t into a place where we can isolate it, we have to first isolate the thing with the t. So the thing we're focusing on isolating first is the exponential term, which is something to a power.
How does simplifying the other side of this, so how does making 25 5 help isolate 8 16?
Because we had this multiplied by 5 in the front. So I need to, no, you're fine. So I need to divide, I needed to divide both sides by that 5 to get it over, to get it away from the, yeah, that's exactly what I did. Divided both sides by 5 because I needed to get this away from my exponential term. Where was I? So now that we have t in a place where we actually can isolate it, now we're focusing on getting this by itself. So we're going to have, we can do this all in one step. If you want to divide each piece separately, go right ahead, but you can divide everything at once if you want. You can divide by the 6 and the natural log of 8. If you do it in 2 steps, that's not incorrect. I am slightly rushing, but if you have a question, let me know. So yeah, this one was different because it had that thing multiplied in the front that we needed to get rid of. We'll look at the other 2 next time. So next time, like just to kind of drive it home, this 5 right here in the next one that we'll look at next time, we'll need to get that 5 away as well. We need the e to the blah by itself first, and same thing, we'll need to kick off this negative 5 over to the other side to isolate. Any more questions or concerns? Going once, going twice. Give a second for the chat to catch up. All right, so let's get you guys off the main screen.